Hello everyone, and this is a small presentation on the elective orientation, wavelets and multi-rate signal processing, which has subject code ET723 in the 1920 syllabus. This is offered in the 7th semester. Now, I'll just brief you on a little bit about the syllabus, and then we'll talk about some the subject in whole. So, according to the syllabus, we have 3 credits for this course, so which means we have 3 hours of lectures per week, no tutorials and no practicals. Okay, as regards the marks, internal assessment is 25 marks, which are your ITs, and there's no term work and 100 marks theory paper. uh, Now, we'll quickly go through the course objectives. It may not make sense at the moment, okay, but nevertheless, we'll just see what this is all about. So, the course objectives are the students will have the ability to analyze signal in the time and frequency domain, an understanding of orthonormality, sampling rate conversion, and short-time Fourier transform, an ability to perform multi-resolution analysis using filter banks, an understanding of various continuous and discrete wavelet families. Okay, so these are the course objectives, and the course outcomes is explain the applications of orthonormal basis in signal transformations, design a filter bank for analyzing signals, perform multi-resolution analysis of a signal using the R wavelet, identify the importance of vanishing moments in construction of wavelets. Okay, now I just read through the course objectives and course outcomes, which may not make sense as I said right now, but once you actually take up the course, okay, things will become more clear if at all you decide to. In unit 1 basically deals with, now the subject is called as wavelets and multirate DSP. Okay, so in unit 1 we have multirate DSP, and unit 2, 3 and 4 basically deal with wavelets. Okay, so in unit 1 we have introduction to transforms, it's basically revision of DSP, Z transform, Fourier series, Fourier transform. What you've not done probably is the short time Fourier transform, which we will look at in this unit. And we'll also take a look at rate converters, that is converting, changing the conversion rate. Okay, that is a decimator and interpolator, either increasing the rate or reducing the rate of conversion. And at the end of this module, we'll look at the disadvantages of Fourier transform and short time Fourier transform and the windowing methods. So this unit basically deals with multi-rate DSP. In unit 2, we look at the wavelets. Okay, from here we talk about wavelets. So we look at, first we look at the Haar wavelet and MRA. In unit 3, different families of wavelet, and we look at some applications of wavelets in data compression, basically fingerprint and the JPEG 2000 standards. Okay, and then we have something called as the uncertainty principle and the challenge and how it is taken care of. In unit 4, we look at 2 important wavelet transforms, that is a continuous wavelet transform and the discrete wavelet transform, and why was there need to switch from continuous to wavelet and what are the advantages and disadvantages. So this is basically what the syllabus is in wavelet and multi-rate signal processing. Now what I did was, I do not want to go into details in explaining the syllabus, so I just thought I'll give you 2 examples of where multi-rate signal processing is used and where wavelet is used. Before that, these are some of the textbook and references that we probably have to go look at when we take up the course. The prerequisites for this subject is a basic fundamentals of DSP or signal processing. Okay, so what is the purpose of studying multi-rate DSP? Now I've taken a simple application in sound. Okay, now we know that the sound range, okay, the audible range of sound is from 0 to 20 kilohertz, right? So now when we are sampling sound signal, we, if you remember the Nyquist rate, we always consider it to be more than 2 times the maximum frequency. So if 20 kilohertz is the maximum audible range, obviously our Nyquist rate is going to be 40 kilohertz, right? So that is the minimum sampling frequency that we need to take. However, when we record onto compact disc, the sampling rate is usually taken as 44.1 kilohertz, And furthermore, when you talk about advanced recording, okay, when recording is done in studios and high resolution recording, it is usually done at 96 kilohertz. Okay, so it is oversampled at the rate of 96 kilohertz. So from 440 kilohertz, at the actual rate at which the sampling takes place is 96 kilohertz, right? So if we are looking at all these different sampling rates, 40 kilohertz, 44.1 kilohertz, and 96 kilohertz, it obviously means that the same sound is being played or is being processed at different frequency rates, right? So it definitely makes conversion necessary from one frequency rate to another frequency rate, right? So multi-rate signal processing is applicable here, wherein you need to change the conversion rate from one to the other, right? So this is one simple example that I thought of. I'll give you as an application to multi-rate DSP. Of course, the applications are numerous. Okay, even in our computer systems, there are many. When we talk about a microprocessor, okay, a microprocessor has a certain speed with which it processes data, but it's not necessary that all the peripherals interacting with the microprocessor are working at that speed, right? For example, a CD drive, which we hardly use nowadays, but a CD drive, or if you talk about a hard disk, they read and write data at a particular rate, whereas a microprocessor works on a different rate. So to communicate from between both these devices, the microprocessor to the hard disk or the CD drive, some rate conversion has to be made, right? It has to be converted to avoid conflicts, to avoid loss of data. Okay, so multi-rate signal processing is used in such applications, right? Very crucial. So this was one of the applications. This second application I thought of was in explaining about wavelets. Okay, now we have already studied Fourier transform, the DFT, the discrete Fourier transform, and we've studied FFTs, right? Now, basically, the traditional Fourier transform, okay, that uses decompositions of sines and cosines, basically gives a global average over the entire signal. Okay, so what happens in this is, if your signal has a similar pattern throughout, okay, the Fourier transform would be a best option, right? But what happens if your signal is um, exhibits different patterns throughout its length, right? For example, if you look at this ECG signal that I've shown here, the PQRX complex is only present in these peaks, right? And the between two complex there is some flattened data over here, right? So if we take the Fourier transform of considering all the entire length of the ECG signal, yeah, it would obscure this data because it's the Fourier transform is considering is basically like an average of the entire length, right? Which may not be very accurate because only the PQRS complex is basically only in these parts, right? So for this reason, we make use of wavelet transform. Now, wavelet transform is a special localized transform wherein you use wavelet is like a small wave, okay, like a small wave. So you take a small wave and superimpose it over the entire length. Okay, it's like very similar to convolution. Okay, you superimpose it over the entire length and you slide it over the entire waveform, and this would give you a better picture and be able to it would be able to analyze the signal in a better way. Okay, so this was a very general explanation that I give you. Of course, the mathematical form is a little different. So a wavelet transform is definitely a better option when studying or when analyzing such signals that do not have the same pattern throughout the length, right? Another thing is that the wavelet transform can extract local, spectral and temporal information simultaneously. Spectral and temporal. Spectral is frequency, temporal is time. So if you recollect in normal signal processing, we could either analyze the time domain or we could analyze the frequency domain separately, right? We can't do it together simultaneously. But wavelet transform allows you to view or to analyze time and frequency domain simultaneously in real time as and when the signal is uh, extracted. Okay, so this is another main thing about wavelet transform. So that's what I had to explain, right? If you have any doubts or if you have any more questions, please feel free and come to meet me anytime, right? So thank you, and that's about it.